Hi friends, this is Dr. G. Srinivasa Gupta, Professor from Department of Mechanical Engineering of VIGNANA JYOTHI Institute of Engineering Technology. As a part of Dynamics of Machinery course, today we are going to see some numerical problems on balancing of rotating masses, both static and dynamic balancing. In previous lectures, we have seen that what is the static balancing and what is the dynamic balancing. As you know that in static balancing of rotating masses, all the rotating masses, the force due to all the rotating masses, that is mr omega square, algebraic sum of all these forces must be 0. If there is any unbalance, then the shaft tends to bend and vibrate and noise is the result. So we need to balance it. So how to balancing in static loading conditions? We will see what is dynamic balancing. First let us see method of static balancing. Static balancing only force balancing. All the forces due to rotating masses need to be balanced. There are two methods we have already seen, graphical method and empirical method. Graphical method, we need to draw each force vector with its orientation properly, and if it forms a closed loop, polygon, loop or polygon, then we can say these are under balance. If it is not forming closed loop, then the closed side indicates the resultant of these forces. We need to use the force equivalent to that in opposite direction of its orientation. We will come to know through some numerical exercises. Empirical method, simply because different forces are having different orientation with the reference axis, whichever we choose, then we see that the resolving components of these forces with respect to reference axis and perpendicular, that all the algebraic sum of these components in any direction must be 0. Then it is under balancing. Otherwise, unbalanced result, whatever it may be, that should need to be balanced by incorporating a mass with a chosen radius. So how we can calculate this, we are going to see soon. Then dynamic balancing, we need to see the balancing of all the forces of rotating masses and also couples generated due to this rotating masses. Both need to be balanced. So algebraic sum of all the forces mr omega square and couples mr omega square L. L means the distance between the force acting in the plane and the reference plane through which we are calculating moment. Here omega square term need not worry, because all force terms contains omega, force and couple terms. So omega square is scaled down. Okay. So here also these methods can be used. If any unbalanced forces or unbalanced moments are there, we need to balance it accordingly. Okay. So this is the difference between static and dynamic balancing. As we know that only forces need to be balanced in case of static balancing, and forces as well as moments also need to be balanced if at all there is no some unbalanced force or moment is exists. So number of planes, if in case of dynamic balancing, different forces are rotating in different planes. If it is single plane, static balancing is enough. Because different planes, it leads to creation of moment also. Okay, conditions are these, we know that. Then we need to remove unbalanced force by incorporating a mass equivalent to that in opposite direction. Similarly, unbalanced couple, if in case of dynamic balancing, we will see how we can do that. And this static balancing is simple, very simple to understand, and dynamic balancing is a little bit more complicated. And applications, if single mass is rotating, there are like grinding wheels and pulleys. And in case of dynamic balancing, crankshaft along the length carries different masses at different planes, turbine rotor also. So these are the examples for in case of dynamic balancing. Okay, as summary you have seen, static balancing requires only force resultant, you have to check that is 0 or not. Dynamic balancing, both force resultant and couple resultant need to be checked. Okay, so it is essential for high speed machinery especially. They create lot of noise, vibrations and failure. Okay, fatigue on the shaft also. So let us take a simple problem on when a single mass is rotating in plane, how we can solve this problem. Here in this case, this problem, a shaft carries a single mass only. You say this is the mass, unbalanced mass. Then how do we make it balance? Okay, when unbalance arises, the mass center of the any mounting element on the shaft is not coinciding with the center of axis of rotation of shaft, then there will be a unbalance somewhere. That is okay. So here given mass 10 kg mass, m is 10 kg, rotating at a radius of, this is unbalanced, it is directly saying that it is unbalanced, rotating a radius of r 200 mm, it is to be balanced by another mass of radius. So balanced mass radius is given, but how much balanced mass required, it is not given. So as we know that algebraic sum of all the balancing masses, m1 r1 plus m2 r2, okay, plus etc., which whatever number, here two only, one is balanced mass, second one is whatever the mass rotating with radius of given radius 200 mm. So to balance it, algebraic sum must be 0. From this we can find what is m2 required balancing mass. Of course, if you write the equation like this, algebraic sum, you will get a negative value. Now, negative in the sense the force is negative. Negative in the sense opposite direction. Opposite direction means with the whatever calculated radius, here you can see written m on r1 equal to m to r2. You got m2 is 13.33 kg. So in this case, you have to mount that in opposite, because this is the force in this direction, centrifugal force in the at this position. Okay, configuration. So opposite direction you have to use m2 mass. With the radius is already given 150. Based on that only we calculated m2 using this equation. So that is simple problem. Okay, we can understand a mass, single mass rotating in attached to the shaft and rotating. Okay, so then now coming to two rotating masses. Okay, this shaft carries two masses, rotating mass, 5 kg one at 100 mm radius, and angle of inclination also given. So this is carrying 5 kg and inclination is okay, this shaft here, this is the mass. Okay, inclination 0 I have taken, that is 5 kg. 5 kg. Radius of rotation is given 100 mm. And 8 kg 90 degrees. Here another mass. Okay, I am going anti-clockwise direction, positive. Okay, direction. So 90 degrees. Here another mass is 8 kg. Okay, 8 kg. So radius of rotation is it is given. Radius of rotation 8 kg is 1200 mm. Sorry, radius of rotation is 150 mm. This is 150, this is 100, right? Okay, so then as usual MR we have to verify M1 R1. This is if you say 5 into 100 plus 8 into 150, that is algebraic sum of M1 R1 plus M2 R2. Okay, that is you have to verify, and we here both are known. Third mass how much is required? If you calculate using this M1 R1 plus M2 R2, you won't get 0. So that is the resultant you will get. That resultant R, let us say, this R must be equal to third mass we are going to use at radius of RB distance. That radius also, in this case, let us see. Okay, this is analytical method, which is components have been taken because the angles are given. So you can use this way all horizontal components of these forces. So M1 into R MR. So M R cos theta. MR is 500. M1 R1 500. So M1 is 100 and R1 is M1 is 5 and R1 is 100. MR is 100 already. MR cos theta. So 500 cos theta plus this second one is 8 kg and 150. This is MR is M2 R2 is 1200 cos plus cos theta 1200 cos theta. Okay, so here theta For theta 1, let us say here theta 2, let us say second one. Theta 1 is 0, theta 2 is 90. So from this we will get okay, total horizontal component of the components of this force is 500. Similarly, vertical components, if you write a similar way, m1 r1 sin theta 1 plus m2 r2 sin theta 2, then you will get all vertical components algebraic sum is 1200. What is the resultant? Resultant is square root of horizontal components whole square plus vertical components whole square, as you know that from engineering mechanics fundamentals. So resultant you can calculate. So R you got 1300. This is MR value. Okay, so this much balancing mass is required because this MR, sigma MR, vertical as well as horizontal components and resultant is not given 0. So you need to use some mass. It is asked in this problem. You can see in this, this is, what is asked in this? Find the magnitude and position of the balancing mass placed at radius 200 mm. 200 mm distance, what is the mass you can place? What is the magnitude? Okay, and what is the direction also, orientation also. So how do you calculate magnitude? This resultant equal to the mass, balancing mass we are keeping in the position and radius with which this mass is rotated. Then this radius is mentioned in the problem itself, that is 200. So you will get balancing mass 1300 by 200. So you have 6.5 kg balancing mass. But what is the orientation? Orientation you will get theta equal to tan inverse, you know that all vertical components by horizontal components of forces. This is 1200 by 500. So you can get theta value. At this orientation, 67.38 orientation, you need to use this. So I will draw diagram again. This is vertical M2 R2. This is M1 R1. This one. And 67.38 means you are going to use balancing mass in this direction. That is MB. This is RB distance. That is center to this radius of rotation, it does mean. So at this location you have to use the attach the mass, then it is 67.38. Then it could be balanced because analytical method directly you can solve like this. Graphical method also, so you can verify all these three masses. If you draw the force polygon, all these together will forming a closed polygon or not, you can verify. Then if forming closed loop, then it is balanced. Okay, otherwise it is not balancing. So your calculations are correct or not. Graphical also you can verify. So finally balancing mass is 6.5 kg and the position is that is this is the resultant you got 67.38 resultant. Opposite direction you have to keep this. This is resultant of these two actually basically. So where you keep this your balancing mass? Opposite direction. Okay, you can instead of these two you can say this is the resultant. Then balancing mass should be placed opposite direction. Are you able to understand? I think. Okay, this is resultant only. You need to understand this is resultant of these two. So balancing mass need to be opposite direction. Then only it is balanced. Are you able to understand or not? Okay, in the calculation. Okay, so then if we go for 3 rotating masses, same procedure you need to apply, and you have to see first sigma MR is going to be okay, analytical method. Let us follow now on what's analytical method. So M1 R1 cos theta 1 plus M2 R2 cos theta 2 M3 R3 cos theta 3 is giving okay 0 or not. It is not giving 0. Obviously in the problem it is said find the balancing mass at radius 150. So it is not giving 0. You will have all the horizontal components sum, algebraic sum, some value, and vertical components also it will give some value. So same procedure you have to apply. You have to find the, because here 3 masses. So let me draw just a diagram. Here 0 degrees here on mass, there is a reference point. This is the radius. What is the 100 mm? So 0 degrees, this is M1. R1 is the distance. And the second one is 120. 120 means okay. Okay, let us say 120, 120. 120 means here it is attached. What is that? 6 kg and 150, 120 degrees. This is M2, let us say. This is M1. M1 is 4 kg, radius is 100, R1. M2 is 6 kg, radius is 150, R2. M3 is at a distance 240. 240 means again 120 to this. Okay, this is 90, 120 to this, right? Okay, here M3. M3 is 5 kg, 200. This radius of rotation is 200. So, how do you find the resultant of all these? As similar procedure. Okay, sigma M R cos angle should be how much? Similarly, sigma M R sine of, okay, each force component how much? These two you will get. This is horizontal one equivalent to horizontal. This is vertical component. So, resultant square root of sigma s square, sigma v square. Then the angle orientation of that resultant is tan inverse, okay, sigma v by sigma h. Orientation you will get. So finally mark that. Let us say I got this one orientation after solving this problem. This is the resultant of this. Okay, and where do you attach the mass at a distance of 150? This is 150, but mass is, because this resultant is R equal to your balancing mass MB RB. RB is given, MB you can calculate. Okay, I think you are able to understand. Then that MB is attached exactly opposite direction of resultant. Then that is at a radius of 150 given. This is 150. You are able to understand, I think. This problem, let us see whether it is, it is already solved, this one. See here, you got horizontal components minus 550. You got minus 550, see here. Vertical minus 550 means, okay, minus value, direction is opposite. It does mean total resultant one, horizontal component. Okay, negative to x direction, let us say. Vertical components you got minus 86.6. Then resultant, square root of, here square root is not written, here square root of resultant is where, here some square root of minus 550 whole square plus 86.6 whole square, or you are going to get 556.8. So this is equal to balanced mass into radius of rotation. So balanced mass you will get 3.7 kg. And orientation also you can find, as I mentioned, as I explained, just like this. Okay, sigma here it is not just written orientation. So tan inverse theta equal to tan inverse sigma v by sigma h. Theta, once you get with that orientation, you can show the resultant. Then opposite to that, this MB, how much you got? This MB is 3.7 kg. You can attach 3.7 kg opposite direction, exactly, because force need to be opposite to the resultant. Okay, these three equivalent to this resultant and opposite force. Then it is balanced. Okay, three masses, rotating masses, balancing how you can do. Like that, any number of masses you can do. If it is in single plane and rotating, then you follow the same procedure, sigma mr equal to 0. You can solve for unbalanced mass and orientation also as well. Okay. So this is four masses rotating, same procedure. Here the problem is mentioned that one mass is not known, fourth one, but it is said that four masses are arranged. Find M and its angular position such that it is maintaining balance, static balancing. So maintaining balancing means right side quantity is 0, sigma mr equal to 0. So fourth mass in that equation, you can sigma mr equal to 0, or components also if you write, you can write sigma mr, okay, cos theta component should be 0, because you need to find unknown mass by writing this equation, sin theta equal to 0. In these equations you are going to get in terms of m, and some theta of that fourth mass is unknown. So two equations, two unknowns, you can solve this one. Okay, for m and that theta. Okay, r is given, right? I think you are able to understand. And if you solve this, you will, what is the calculation procedure? All mr values you tabulate, and then Okay, resolve components x direction, y direction, find resultant, and you can find fourth mass. Okay, and you can get this answer is given. You can check it by solving same procedure. You can check it. Mass you are going to get for this problem 5.8 kg and position 310 degrees. That mass M4 position is 310 degrees. Then the system is entirely in balancing. Coming to the dynamic balancing, as you know that dynamic balancing, what is the additional condition we need to verify? It is not only sigma mr, all the force quantities 0, algebraic sum, and sigma mr L also. So means the masses are rotating in different planes. Dynamic balancing arises when the different masses are rotating different planes. Here in this plane some masses are there, in this plane some masses are. Even though forces are balanced, suppose the resultant of all the forces is in this direction and resultant of all the forces in this plane in this direction. Let us say resultant here R1 plane, R2 plane, resultant. So force balance is, because let us say R1 equal to R2 you got. For somehow these forces, given forces, here also some forces are acting in different planes. Then force balance is balanced because it is opposite direction, exactly equal magnitude. But these lead to couple in the plane. Okay, this is a perpendicular plane. So that couple leads to unbalance. That shaft will wobble. So what you need to do is, these two need to be balanced. So how do you do that? Force balance equation, couple balance equation you need to write, and if it is set balanced, then write that couple equation also for all the forces. Then you can find unknown quantity. Balanced means that sigma MRL, use this relation, is 0. If you take moments about one plane, any one plane, this one or this one, this only one term will come, MRL of this resultant force. This becomes 0 because with respect to this you take moment. Then that quantity you can find. I think you are able to understand. If you take moments about this quantity you can find using this equation. So in detailed problem we will take and discuss in our coming next lecture. Thus overall we can say that okay, two equations must be satisfied in case of dynamic balancing. One is force balance equation and couple balance equation. Okay, so in graphical method if you want, it's very easy, but you need to take care while taking scale or everything. So you need to draw force polygon and couple polygon, and you see that these two must be closed, and closed side you measure, and that is equal to your MRL from the couple polygon if you take. Then that whatever unknown M that can be, you can calculate. So with this I am concluding this lecture here. More discussion on dynamic balancing problems we will see, and its practical applications also we are going to discuss in detail. Okay, thank you one and all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.